Michel Boileau in joint work with Stefan, who I think has already had to leave, unfortunately.
So, at his invitation, it's a pleasure to be in Isaac Newton Institute. Today I want to speak about, some kind of classical three-dimensional topology, which is a study of epimorphism between free manifold groups. So, I will just, so in my talk, all free manifolds will be compact, orientable, aspherical, so it means that they are KP1, and also the other characteristic will be 0. That means that the boundary is either empty or an union of tori. So when I speak about manifold, I will say that. And now I will look to proper map from M to N, which means that if the boundary is empty, it will be goes to the boundary of N. And I will say that F is a proper pi1 epimorphism if it induces an epimorphism at the level of the fundamental group. So, will be surjective. So, because of the geometrization, I will say Perelman geometrization theorem. We know that the fundamental group of free manifolds are residually finite. And so in some sense, having some epimorphism from pi1m to pi1m will give an ordering. So it's a partial order. So the existence of an epimorphism from pi1n to pi1n will give a kind of will give a partial order. So we can say that M in some sense is bigger or equal to N. And it's a partial order because, you know, it's pi1m is residually finite, so any epimorphism from pi1m to itself will be an isomorphism. So in some sense that gives the fact that it's antisymmetric. Okay. So the question will be how you can, in some sense, what will be the relationship between the invariant of N and the invariant of M? What are, in some sense, the good invariant? So good invariant will be invariant which are, in some sense, so I will say good invariant will be invariant sigma of M such that if you have this epimorphism, then so the prototype of this invariant is the rank. This example will be the rank of pi1m. So the rank for me is the minimal number of elements you need to generate the group. So it's not yet here. So example of proper pi1 epimorphism, the perhaps best example is this degree 1 map. That's a proper map and which induce an isomorphism at the level of the H3. So since the fundamental class to the fundamental class. And the degree 1 map is known to be an epimorphism. There is a big difference between proper epimorphism and degree 1, in a sense. But the statement I will give works with proper epimorphism. Even if starting with proper epimorphism, you already have this partial order. But it will be different from the partial order you get if you look to degree 1 map. So the problem of rigidity would be you have a map like that, you look to an invariant and you would like to find extra condition which ensures that this is homotopic to an homomorphism. So the prototype of result for this is this Gromov-Thurston result using volume. So I define the volume as the sum of a manifold as the sum of the volume of the hyperbolic pieces of the geometric decomposition. It's the same, in some sense, up to a constant than the simplicial volume. And this result of Gromov and Thurston is strengthening of Margulis and Mosto rigidity theorem. If you have a degree 1 map between two hyperbolic manifolds, it will be homotopic to a homeomorphism if and only if they have the same volume. So in some sense, it's a wonderful result, but it's not really what we want, because here, the condition that they have the same volume does not involve F. It just say, okay, if you have the same volume, if M is bigger or equal to N, it must be N, okay? This result, if you take the result like that, it works in any dimension, bigger or equal to 3, but for three-dimensional manifold, the result has been generated by Soma, and Soma shows the following. If you take a degree 1 map and if you assume that vol M equals vol N, then F is homotopic to be a homeomorphism on the hyperbolic pieces. So that means that to understand then the degree 1 map, you only have to understand what happened on the Seifert pieces. And the study of degree 1 map of Seifert pieces is much easier. So using this Soma result, for example, in Gromov-Thurston, you can assume only M or N to be hyperbolic, and it will still work. The best, perhaps, generalization of this kind of result is due to Derbez. We really gave a necessary and sufficient condition for degree 1 map to be a homeomorphism, but using this bounded cohomology. So Derbez result states that if you look to your degree 1 map, then you look to the induced map from the bounded cohomology of N to the bounded cohomology of M. I will not recall it, but bounded means you have a norm on the class. If this is an isomorphism and more than that an isometry, then F will be an isomorphism. It's very nice in some sense. So from the bounded cohomology, you get the volume, simplicial volume. From the bounded cohomology, you get also the Thurston norm, as Stefan Friedl was speaking about the Thurston norm. So it's something stronger, and it's a cohomology of group, but it's difficult to compute. I mean, if you take the second bounded cohomology group, it's usually an infinite dimensional Banach. So it's not really, really what we would like. It's not easy to use. So looking to another kind of rigidity, there have been a lot of activities around this profinite completion and so on. So okay, you could say, okay, I look to two free manifold. Can I decide if this epimorphism is a homeomorphism, is homotopic to, is a bijection, so it's homotopic to homomorphism, looking to the finite quotient. And in fact, it was an old result that it is true that if your two manifolds have the same set of finite quotient, so the fundamental group has the same set of finite quotient, then F must be must induce an isomorphism, so must be homotopic to homeomorphism. So the key point here is that when you have the finite quotient, you have some preferred finite quotient. So you have your group, and you can look to the characteristic subgroup, which is the intersection of all the finite index subgroup okay? And then when you look to this quotient, this is characteristic. That means if you look the set of finite quotient, this one will be the smallest finite quotient which surject on all the finite quotient with cardinality smaller or equal to n. So if your two manifolds have the same set of finite quotient, they must have the same characteristic quotient. And that's exactly what happened. So here you will have the same characteristic quotient. So you look your epimorphism, it will induce an epimorphism between this characteristic quotient. But since they are finite and the same cardinality, it must be an isomorphism. Then when you look to the kernel of your epimorphism, it will induce to the kernel of this epimorphism. But because here you have an isomorphism, the kernel of this epimorphism is exactly the characteristic subgroup. So the kernel of your original epimorphism is induced in the intersection of this characteristic subgroup, which is 1, because your group is residually finite. And so you get that this epimorphism here is injective, and thus an isomorphism, and that from the geometrization it will be homotopic to homeomorphism. So that's better because in some sense, if you believe that it's not an isomorphism, then you can check it on finite quotient of the fundamental group. What is not good is if you have to check both pi1n and pi1m. So it will be better to have a criterion where you work only with the finite quotient of, say, the target. So that means when you work with covering finite cover of the target. And that's exactly what did Perron-Chalène and then Derbez. That now I want to use more basic invariants, which are integer, either the Betti number, either the rank, either the heegaard genus. So a map is a homology equivalence if it induces an isomorphism at the level of integral homology group. And this theorem of Perron-Chalène, and it's fair to cite Aschenbrenner and Friedl because there was some problem in the proof here that they fixed. And then Derbez generalized to any manifold. It tells that if you take a map F from M to N, which is pi1 epimorphism, when you have a finite group and you take the finite covering, then the map here surject also to this finite group. It's a finite, I will say, you have a finite covering. Then you can pull back the cover, and the idea is to compare now, for each of the finite cover, to compare these two elements. And the result says that when the lift for each of the finite cover here give me an isomorphism at the level of the homology, then the manifold F must be homotopic to a homeomorphism. So the result of Perron-Chalène works for graph manifold, and they prove it for graph manifold, where the volume is both 0. And then it had been extended by Derbez, but with the hypothesis that the volume are equal. This hypothesis is not good in some sense because it's difficult to verify that the volume are equal or not. Okay. And the second thing is that if you withdraw this hypothesis, the theorem is no longer true. So there is a way to, given any tower of finite cover, of a finite cover, so say N1, N2, then you can always find a cover with hyperbolic manifold. And at each level you have the homology equivalent. So it shows that there is nothing specific to hyperbolic manifold when you look tower of covering. And what you can realize in some way, you will realize by hyperbolic manifold. And in general, there is no homeomorphism. And so when you don't have this hypothesis on the volume, then you can find examples of two manifolds with different volume, and such that you have this induced the homology equivalence. So the idea is to use the new result and very strong result of Jan Hegel and Pretzisky, Weiss, and Weiss about the virtual vibration theorem to show that you can get some criteria using more basic invariant like the rank or the heegaard genus. So the goal of the talk is to prove the following result. So we can use that what we call the subregular covering, which is just a composition of regular covering, but okay. In the previous result, you need to state the hypothesis for all the covering. You cannot choose some special one. You need to put the hypothesis for any finite covering. Here we can reduce to subregular, and the rank of M will be the rank of its fundamental group. And as I said, if you have a pi1 surjective map, then you have this equality on the rank. Now the result says that if N is not a closed graph manifold, that you understand where is the hypothesis. If it's not a closed graph manifold, then by this virtual vibration theorem, there is a regular finite cover which fiber over the circle, and that will be the key point of the proof. Then you take a proper epimorphism. It will be homotopic to homomorphism if and only if, when you look to the finite cover, any regular finite cover or subregular finite cover of n, and you look to the induced cover, they must have the same rank. So at some point, if it's not homotopic to homeomorphism, the rank has to blow up. So before coming to the proof, there is a variation using the heegaard genus, which is in some sense more interesting because if you have this proper pi1 epimorphism, it's not true that the heegaard genus of the domain is bigger or equal to the heegaard genus of the target. It's false, in fact. If you have degree 1 map, it's still an open question. It was a dream to prove the Poincaré conjecture, but it's still an open question, I mean. But for proper pi1 epimorphism, it's wrong, I mean. You can build here closed, because if you have closed manifold, any map is proper. But so here you can build closed manifold with epimorphism on some, say, hyperbolic manifold, and such that the difference, the heegaard genus here is strictly smaller than the heegaard genus here, and even you can do the discrepancy as big as you want. And the construction is just based on the fact that Pauli shown that there are hyperbolic manifold where the rank is strictly smaller than the heegaard genus, and you can make the discrepancy as big as you want. So in some sense, here the algebraic property will not be sufficient to ensure the inequality of heegaard genus. However, it's virtually true. So it's it's virtually true and not difficult to show that if you pass to some finite cover, then the inequality will hold. So it means that in some sense you take your example where here you have this F, and here the heegaard genus of M is largely smaller than the heegaard genus of N. But going to some finite cover induced by the same group in some sense, then here the heegaard genus of M will be bigger. So it shows that the behavior of the heegaard genus by finite cover may be tricky in some sense, and really depend of the manifold. Okay, so as I said, the key point for the proofs is really this Hegel-Prediski wise and wise result that prime free manifold with empty or toroidal boundary that is not a closed graph manifolds. Graph manifolds are unfair in some sense. They resist, they are not finite covered by the surface bundle. I must say that for graph manifold, I don't know if the result is true. So this, let's see. So this one, I don't know even if this one is true for graph manifold. It's clearly true if n is a Seifert manifold, easily, but for graph manifold, I don't know.
What if it's a graph manifold that is a surface bundle? Because they can be.
It can be, no.
Does your proof go through?
So if it's a surface bundle, we win, but you have graph manifold which are never covered by surface bundle. That's the one which does not carry non-negative Riemannian metric. So if you have if the boundary is non-empty, it's always virtually a surface bundle. Then if it's closed, the condition is more subtle, but you have a Riemannian condition that if it if it carries a Riemannian metric with non-positive curvature, then let's see. Yeah, it will be a surface bundle.
And you win.
Yeah. So but at least, you know, the big problem is all the examples where the rank decrease strictly with respect to the genus is examples that you obtain by gluing pieces along incompressible surface. Graph manifold, when you go to the covering, it's difficult to handle the gluing and to see if you will not reduce at some point this heegaard genus or this rank. And so the case of graph manifold is not easy. I believe that it must be true. I believe that because I believe that generically the GSG is compatible with the Morse function associated to the heegaard genus. Compatible for me means that the GSG tori has to be in the level of the Morse function. And I guess that generically GSG behave well with respect to Morse function. And I mean, especially if it's a minimal genus and so on. But I have no proof of that. Okay. What was the key point? So, just to be short, the key point is the following fact, that take n, say, surface bundle with monodromy phi, then you know things. You know that the rank of pi 1 n is smaller or equal to twice the genus plus 1. That comes directly from the computation of the homology. And you know also that the heegaard genus of n is smaller to twice the genus plus 1. And that's come only from the fact that you have your bundle, you thicken the surface like that, and then you put a tube, a vertical tube here, and another handle here. And so here I have a surface cross I, and I add one handle, and I get this handle body of genus 2G plus 1, and here also. So in some sense, you have this kind of inequality, and it happens easily that if you take a sufficiently high cyclic cover of n, you will have equality. And this is just a stupid remark, which was well known, is that if you look to the, with Z2 coefficient, whose cardinal is finite, and so there exists n such that the action of phi n is, or acts trivially on and the bound on n is depends only on the genus. But if it acts trivially and you compute the dimension over Z2 of H1 of this will be exactly 2G plus 1. So you win. Then it implies that the rank of this equals the heegaard genus. And this is the maximum. Okay. So this is the key point. So you take your manifold N, you go to the first regular covering where it's a bundle, and you take a second cyclic covering, and then you have a cover, subregular cover of your manifold, where everything is maximal. Okay. So you could say, why putting so many hypotheses? Let's see, come back to this one. Why putting the hypothesis that the rank is the same for every induced covering? Now, what you would like is to come to the situation where you have a surface bundle here and a surface bundle here. But you know, when you look to the induced cover like that, you have to ensure if you get a surface bundle here, there is no reason why to get a surface bundle here. And the condition on the rank will allow to ensure that. So we will get that by going to sufficiently high covering, we will get a tower of covering where we will have at some point surface bundles here and here. And then using the rank condition, we will be able to show that at some level it will be an isomorphism, and then if it's isomorphism at some finite cover, it will be isomorphism downstep. So that's a strategy. It's not difficult. So here is the proposition, which I more or less proved. You take a free manifold, you take a homology class, cohomology class. You take the cyclic cover induced by this cohomology class. And we will say that the cohomology class is fibrate if it corresponds to the projection of a fibration over the circle. And then you have this, what I just showed. If you take a fibrate class, then the 1 plus rank of the curve phi, which is the rank of curve phi is twice the genus of the fiber, is smaller or equal to the rank of the bundle, which is bigger or equal to the dimension of this homology group. And then, as I show, there exists for n, some n, there exists an integer n such that you have equality. So here you can take p equal to. It works for NAP, but you can take p equal to. So that's a well-known proposition. So now the proof is, as I say, you have the fiber corresponding to the, no, this is the proof of the proposition, but this is an exercise. So, sorry. So now, here is the tool we will use to detect bundle. So you have this rank gradient. This notion of gradient has been introduced by Mark Lakenby, and you look to the rank of this cyclic cover, and you divide by the degree of the covering. And you have this following very nice result that says that if you take a cohomology class, it is fibrate if and only if the rank gradient is 0. So this result has been proved first by Lakenby. It has been proved not for the rank, but for the heegaard genus. So Lakenby proves that if you take a class like that, and you look to the heegaard gradient of the associated cyclic cover, then it's a fibrate class if and only if the rank gradient is 0. And you can see that if you are in this cyclic cover, you never change the genus of the fiber. So the rank or the heegaard genus stay bounded. So Lakenby conjecture, which is still open, is that if you have a tower of covering where the, I will say the genus gradient is 0, then you must find in this tower some bundle. But this is not known. Even if we know the virtual bundle theorem, this is not known that in a given tower you can, when can you find a surface bundle. The only result in this direction was by Claire Renard in his thesis. But she has a log n, not a n result. So this implication was immediate. I mean, here it's not trivial at all, and it's based on this result by Friedl Vidusi that twisted Alexander polynomial will detect if manifold is fibrate or not. So it's really based on computation using Reinmeister torsion. Okay, so now we can make the proof. So you have this proper pi1 surjective map. You first go to a finite cover which admits a primitive fibrate class, which is a bundle. And you look to the induced cover for M. And now you start looking to cyclic covering of N tilde, which is induced by the class. And you have the corresponding cyclic covering of M tilde. Then the fact that the rank are the same shows that since phi is a fibrate class, the rank gradient of pi1 n tilde is 0, but it's equal to the rank gradient of pi1 m tilde, because the hypothesis is that this covering has the same rank. And so it means that the pullback of the class must be a fibrate class. So now I am in the situation where I am in the situation where I have n, f. Here I have n tilde, which is fibrate over S1. So I will say and here I have also m tilde, which is fibrate over S1. And by the construction, I know that F tilde is fiber preserving up to homotopy. So I can make an homotopy so that the fiber here is the preimage of the fiber here. Because you know the cohomology class determines the fibration, in fact, up to homotopy, even isotopy. So here, in some sense, now what I have to show is that I have the same genus. If I have the same genus, then my pi1 surjective map will be a pi1 surjective map between two surface groups of the same rank. They are Hopfian, so it must be an isomorphism. And if it's an isomorphism at the level of the surface, then it's easy to show that it's a global isomorphism. So why the genus has to be the same? Let's come back. So the computation of the rank of the surface bundle shows that the rank of ker phi star phi, f star phi, which is twice the genus, is in fact the maximum of the rank of this cyclic covering -1. But the rank of the cyclic covering by hypothesis are equal. So it gives me that the genus here must be equal to the genus here. That comes also from this hypothesis on the rank. And now if the genus are the same, then as I say, it's easy to show that you get an isomorphism. And then you get that it's homotopic to homomorphism using either Waldhausen, but here you need that you have a proper map. That's where you need to have a proper map to use Waldhausen work. Or in the hyperbolic case, this is this most hazard rigidity. So there is just a small subtlety. I say proper, so it could happen that M is closed and has some boundary. A priori. So when I say, okay, I have an epimorphism from a surface group to a surface group, and we know that it's an isomorphism, it's true if they are both free groups or both surface group of closed surface. But here, that's the point is that you have this equality, then if the fiber of M has no boundary, that is, M has no boundary, then since it's an epimorphism and you have the same rank for the fundamental group, the boundary of F must be empty. Because when you take a closed surface group, it will have an epimorphism on some free group, but the free group will have a rank which is the rank of the surface group divided by twice. You cannot do better than going from the handle body. So you cannot have an equality. That's the only small subtlety. Okay. So, yeah. So, for the virtual genus theorem, it can seem bizarre because then, as I say, you don't have the inequality. And in some sense, the genus is really something which is topological, and the proper pi1 surjective map, in some sense, for closed manifold, it's nothing to do with topology, a priori. But here, here you have a manifold, then this lemma is absolutely well known. And as I said, if you have a bundle, then the heegaard genus of the manifold is, as I said, smaller or equal to twice the genus of the fiber plus 1. And what makes the things to work is at some point you have equality. So now, what is the things? Either you use Lacanby result, but you know, you have this genus, heegaard genus gradient, and the following proposition, which is true, if you have a primitive class, it is fibroid if and only if this heegaard genus gradient is 0. Either you use the original proof of Lacanby, or it's follow from the fact that the heegaard genus is bigger or equal to the rank. So if the heegaard gradient is 0, the rank gradient is 0. And we know that the class must be fibered. Having that, you pick up the same proof, you follow the same proof, and it gives you the result with heegaard genus. So, let's see if I want to say. So the question that's perhaps more interesting. So, we'll start with a provocative question. So a question, I mean, for me, interesting question is, you take a degree 1 map, M small. Does it imply that the heegaard genus of M is. And in particular, M small, does it imply that the heegaard genus of M equals the rank of pi 1m? I think it's worth asking the question because at the moment I don't see any proof which can handle that. Perhaps I have no idea if it's, I would say because I am pessimistic that it has to be wrong. And if it's true, and if you don't use the geometry, that will give you a proof of the Poincaré conjecture. I will advise to read the proof of Perelman, and then it will be more than I hope it becomes a dream to have a proof which just avoid all the epsilon, except that you will not get the geometrization. But you know, you don't need that. You need something much weaker than that if you want to prove the Poincaré conjecture. Because all the proof for the Poincaré conjecture was not to show that the rank equals the heegaard genus. It was to show that if you have your homotopy sphere and you have this S3 and you have this degree 1 map, you want to show that any heegaard splitting here is weakly reducible. So you have this notion of distance for heegaard splitting, which was given by Hempel, which is to look in the curve complex the distance between the meridian disk in each handle body. And so the goal will be to show that the distance of NA splitting, I will say this, is smaller or equal to 1. If you take a manifold and you look all the heegaard splitting, you look all the distance, there is a max, which will be perhaps the heegaard diameter of your manifold. You have a max. And so in some sense, another question would be, if I have a degree 1 map like that, can I get, in some sense, a bound of dn from some function of h m dn? So perhaps the inequality has to take in account the distance, Hempel distance, and the genus. And working with manifold, you quickly see that, for example, manifold with a big, I will say, Hempel diameter, that is manifold where the distance is bigger than twice the heegaard genus. They more or less behave, in some sense, like small manifold. Because you know, this means that you will have incompressible surface, but incompressible surface with genus bigger than the heegaard genus. And when you look the construction, when you reduce the genus, then the surface appearing are smaller than the heegaard genus, the incompressible surface. So here I think there is some question to ask. So I did not write this kind of question because I have no idea if it's true. I think this diameter will be important in some sense at some point. So here are the question, I mean, so does this virtual rank theorem works for graph manifold? I ask it. I don't know even for Seifert manifold, it's a shame. If the target is a Seifert manifold and I put the hypothesis that for the induced covering you have the same rank, I cannot prove that the domain is a Seifert manifold. It has to be, but. And so does the virtual rank or virtual heegaard genus characterize closed graph manifold? So there is now results which say that the profinite completion characterizes graph manifold. So the finite quotient. You can show also that if you look to the virtual first on norm, you can characterize graph manifold. So you look to all finite cover and you assume that you know what is the first order norm on the homology. And this will characterize graph manifold. But can you characterize graph manifold by this virtual rank? This I don't know. And this, what I said, this proposition is almost trivial. If n is a closed Seifert manifold, then, and you have a proper pi1 epimorphism, then you can go to a finite cover where you get this inequality. It's just because you take a bundle, S1 bundle, and there the rank equals the genus and so on and so on. So this is not. But I don't know if this proposition holds for graph manifold. I will bet yes. Then here is for degree 1. Do you have always this inequality? This is perhaps more reasonable. Is it true that at least a part of the heegaard genus of n survive? That is it true that the heegaard genus of m will be bigger or equal to a constant, the heegaard genus of n, and you want the constant to be uniform? A stronger version will be the same with the rank. We know that the heegaard genus is bigger or equal to the rank, but we don't know if the rank can be much more. It can be much smaller, but not the ratio. This is related to some cost conjecture, I think, by Gaborio. But at the moment is not known, and this wonderful result of Richard Weinmann shows that it is true for graph manifold. And he has 28. That's a wonderful result, and it's just a result about computing rank of a cylindrical graph of groups. And also his proof shows that the general result is just now reduced to hyperbolic manifold. And hyperbolic are virtual bundle over S1, so the first case to look is the bundle over S1. And for bundle over S1, it's clear that you get an inequality like that, but mu will depend of the genus. From what I say, it's clear that you will get an inequality, but this constant will depend of the genus. And so it's not good. But it's still so a conjecture to know if this will happen. So I guess I don't know if I have. This was just to say some word on that, because this was a rigidity result which I like, in the sense that here it's for degree 1 map. You look to your knot spaces and you put the volume as usual, but the genus will be sufficient. There is only one problem. You have to avoid this widening number 0 companion. That is, it does not work for a double knot. Now here is a question. So you have this L2 Alexander polynomial, and I don't know how. We know that Alexander polynomial behave well by degree 1 map. So the Alexander polynomial of the target will divide the Alexander polynomial of the domain. The same with twisted Alexander polynomial with finite coefficient. But for the L2 polynomial, I don't know, except that the L2 polynomial determines the volume and the genus. So if you take two knots with the same L2 polynomial and a degree 1 map like that, if they have no zero widening number companion, they must be the same. I will bet that they are the same even with widening number, zero widening number companion. But how to detect this zero widening number companion with L2 polynomial? And then this question, I believe, it has to be true. If you have an alternating knot and this degree 1 map, I believe that K prime has to be alternating. And this comes, for example, from the talk of Steve. If you have a degree 1 map between two exterior knots, it gives you a degree 1 map between the two-fold branch cover. It extends. And so the twofold branch cover of alternating is not left orderable. So the twofold branch cover of K prime cannot be left orderable. So it will have to be an L space if I believe all the conjecture. And so then it's come nearby some alternating knot. So perhaps this is true, and I believe also that for alternating knots you don't need the volume. The genus will be sufficient. And this is true for many alternating knots. This is true, for example, if the leading coefficient of the alternating knot is a power of a prime. This is due to Cameron, in fact, and use this Stallings exact sequence, and the fact that the commutator of these knots are residually penile-potent. This is a question in general for alternating knot. Is the commutator subgroup residually nilpotent? If so, then this will be true. And this one is kind of, can you even get a condition just by computing the discriminant of the knot? Okay, I will stop there. Yeah.
Further questions from the show? All right, let's thank them again for a great talk.